All right, hi guys. So let's reflect a little bit on the law of sines that we just spent a couple days on. What scenarios can we solve with the law of sines? Well, first off, we solved a couple problems that were angle side problems. So angle side is something that we can solve with the law of sines. Now, one thing I forgot to mention in those videos, if we know two angles, then really we know all three. So if we can solve angle side, we can also solve angle side angle, because in both of those cases, really we know three angles in one side. They're identical, they're just named a little bit different from geometry for our proof postulates and theorems. And then we also saw that we knew how to handle side angle, the ambiguous case, which broke into big side, little side angle, and little side, big side angle. That's the ambiguous case. We had to be careful. There could be 0, 1, or 2 possible triangles if we had that information. So what does that leave us with? What other measurements of a triangle could we be given and asked to solve? Well, thinking about from geometry, my list, I see that side is missing, and so is side, angle side. Those are the two that are missing. Remember, we also have angle. However, that does not guarantee a unique triangle because they're just guarantees triangles are similar, so we couldn't solve for side lengths in that. I also know we talked about hypotenuse leg back in geometry as one of our theorems for proving triangles are congruent. However, that's a right triangle, so we don't even need law of sines or what we're going to learn today, law of cosines, to do. So law of sines cannot be used with side angle and side angle side, or side and side angle side. So we need a new formula for this, and our new formula has to contain all three side lengths. If we go back to law of sines, it was side, angle, side, and an angle, right? There was two sides and two angles, so we could use those combinations. This has to have all three sides in the formula and an angle in the formula, and I'm just going to show you what they are here. Law of cosines can work for side angle and side angle side, and there's three different formulas depending on the information that's given. The first one is a squared, so side a squared equals b squared plus c squared minus 2bc cosine of a. This is called law of cosines because it has a cosine in it, where law of sines had a sine in it. B squared equals a squared plus c squared minus 2ac cosine of b, and c squared equals a squared plus b squared minus 2ab cosine of c. So notice they're all very similar. We're just naming them different. Really, we could have one law of cosines and just change how we name it. But here's our three options. So the question becomes, where does this come from? Where does this law of cosines develop from? How do we figure this out? When you look at this, it should remind you a little bit of the Pythagorean theorem, right? In fact, right here, I see c squared equals a squared plus b squared. All of these remind me of the Pythagorean theorem. So that's probably going to come into play here. So here's what we're going to do. We're going to take our oblique triangle, our non-right triangle. We're going to draw an altitude again, just like we did with our law of sines. Okay. However, I'm going to do things a little bit different. I'm going to put our triangle onto the coordinate plane, where our vertex A is at the point 0, 0. Okay, and that side B is going to be on the x-axis. So this is side A, this is side C. All right. Now, what I'm going to do is I'm going to call this point at B, because I put it in the coordinate plane, as x comma y. And the reason I would do that is it now makes this x and this y. Okay, so we've split it into two triangles. Notice in this triangle it's x, y, and c for side lengths. In this triangle it's a, it's y, and, well, how long would this be? Well, remember, from a to c is b, from a to that point is x, so this is b minus x. Now let's write that Pythagorean theorem like we talked about. We're going to write the Pythagorean theorem. Depends on which of these we're solving. Let's do this one. So we're going to write a Pythagorean theorem that involves a squared. So we're going to use the triangle on the right. And we're going to say b minus x squared plus y squared equals a squared. So that is the Pythagorean theorem for the right of the triangle. Now we're trying to develop the law of cosines. Does the law of cosines have x's and y's in it? No, it doesn't. Okay? We need it just in terms of the angles A, B, and C and the side lengths A, B, and C. So can we figure out what x is in terms of the sides and angles of our original triangle? Can we determine what y is in terms of our original triangle? So here's what I know. Here's angle A, x is the adjacent, C is the hypotenuse of the right triangle on the left, if that makes sense. The right triangle on the left. Adjacent hypotenuse is cosine. The cosine of A equals x over C. So we get C times the cosine of A equals x. If I do the same thing for y, now it's opposite and hypotenuse. We know that the not the cosine, opposite hypotenuse, that would be sine. The sine of A equals y over C. So C times the sine of A equals y. All right. Feel good about that. So now let's do some substituting. We don't need to substitute anything in for b because we want there to be a b in the law of cosines formula. So we're going to go b minus, what is x? X is c times the cosine of A squared. Plus, what is y? C times the sine of A squared equals A squared. And this is what I want to work off of. I should have given myself more room to work. So I'm going to just put this into a new page and we'll go from there. All right. This is an A squared right there. Okay, so what I can do is I can FOIL this out. It's going to give me a b squared minus a 2bc cosine of A plus c squared cosine squared of A, right? C cosine of A times c cosine of A is c squared cosine squared of A. Plus, now, what do I have here? C squared sine squared of A, right? I'm squaring a product, so I can just square each part, equals A squared. All right, so let's look at that law of cosines. We have the A squared part. Okay. Let's see, what else do we have? Notice I have a minus 2bc cosine of A. Minus 2bc cosine of A. I have this part. Let's see here. We also have a b squared. We've got this part. What about this part? I don't see just a c squared there. But what I do see is, I do see the c squared in both of these terms. So what if I factored out the c squared in both of these terms? What does it leave me with? Cosine squared of A plus sine squared of A. And I have a cosine squared plus a sine squared. And what do I know about cosine squared plus sine squared? Pythagorean identity. This is equal to 1. Okay, so we have b squared minus 2bc cosine of A plus c squared times 1 equals a squared. And if I just rearrange a little bit, I have b squared plus c squared minus 2bc cosine of A equals a squared. And that is the first law of cosines law that we have. Now I could set it up and I could do it for the other two. We're not going to do that in this video. Okay, let's get to work. All right, so angle A is 72 degrees. Angle B is 14. Angle A is 72 degrees. Side B is 14. Side C is 23. Let's find side A. Let me just draw a triangle here. Okay. Looks good. Let's call this A, which is 72 degrees. We'll call this B and this C. B is 14. C is 23. There's A. Notice what we have here. We have side, angle, side. A side, the included angle, and a side. So side, angle, side tells us, ba-dum-ba-bum, law of cosines. And what are we trying to find? We're trying to find A, which is the formula that we just proved. A squared equals B squared plus C squared minus 2BC cosine of A. You're going to have that memorized in no time. So let's substitute in. A squared equals 14 squared plus 23 squared minus 2 times 14 times 23 times the cosine of 72 degrees. All I'm doing is substituting right in. So, time to grab my calculator. I'm going to take 14 squared plus 23 squared. So these two, that's 725. Notice sometimes I have students want to type in 14 squared plus 23 squared minus 2 times 14 times 23. However, 2 times 14 times 23 is in a product with the cosine of 72, so we can't combine all of this. Sometimes students want to do that. We can do this part, which is 725, and then minus 2 times 14 times 23 is 644. Cosine is 72 degrees. That's what we have. Now we're solving for A, so we're going to just take the square root of both sides. And we get A is approximately, and now I can just type this in my calculator, the square root, 725 minus 644 cosine of 72. We get about 22.9. Now, the law of cosine, the formula is a bit more expansive than the law of sines. It looks more complicated, and there's times it can be a little bit messier. But one nice thing about the law of cosines is there's no ambiguous case like side-side angle has in the law of sines. The law of cosines is plug it in and just go and solve it. You don't really have to consider too much about what's happening with the triangle. Side, angle, side, and side, side, side produce one unique triangle. We don't have to worry about that stuff like in the law of sines. I'm going to wrap up this video. We've got one more example in the next video to do.